Good morning, Prof. This is Team 18 and I'm Grace. Together with my teammates Michelle, Gary, and Chloe, we will be presenting on our cloud computing project, specifically on federated learning. This is our agenda for today. We will be presenting about our problem statement, our solution, the flow of our solution, our results, and finally our demonstration. So, I will start by talking about our background. As we are experiencing right now in this pandemic, we can see that as the number of COVID-19 cases continues to spread, with more and more people needed to be quarantined and hospitalized, there is an issue with the shortage of healthcare workers. So in order to help relieve some of their jobs, our team decided to implement machine learning to easily discern and identify if a patient is infected with COVID-19. This can be done by performing image recognition of the different types of chest X-ray scans. The different types of X-rays we train are the healthy respiratory system, those who are infected with pneumonia, and those who are infected with COVID-19. As you can see from this X-ray image, those parts circled in yellow are the parts that help us differentiate the X-ray scans between a person who is healthy and a person who is infected with COVID-19. This project can also be done using centralized machine learning, but as there are some disadvantages to it, my team decided to implement federated learning. These are the problems with traditional centralized server. So firstly, for data privacy, the data in the network traffic is prone to interception and is at risk of data leakage. Secondly, machine learning requires high computational power to train models consistently. As such, high costs are incurred to maintain these servers just to store and train models. Thirdly, internet security has always been an issue, and hackers is always finding new ways to exploit servers and extract data. And lastly, a centralized server contains all the data and trained models, and if not maintained consistently, it is prone to a single point of failure, resulting to a loss of data. Thank you. Next, I'll hand over to Chloe to explain about our solution using federated learning.
Thank you, Grace. Therefore, with that said, we have decided to use federated learning as a means to solving our problem statement. There are 4 main benefits of federated learning, first being data privacy and ownership, whereby the data of X-ray scans first undergo training on the local client. This data is not passed on to the server or shared with anyone else. This enables training of shared statistical models based on decentralized devices or servers with a local dataset without the need to upload private data to the cloud or with other organizations. Compared to traditional centralized machine learning techniques that require datasets to reside on a single server, federated learning reduces data security and privacy concerns by maintaining stores of local data. The next benefit would be that a lower computational power is needed. With federated learning, model training is done on each of the local clients and not by the server. Therefore, there will be lesser computational power used for the server and lower overheads. The third benefit is that we can achieve higher security with federated learning. We are able to implement encryption, adding of weights, and using a secure aggregator to achieve a higher level of security, especially in the case of sensitive data such as patient information. Lastly, federated learning allows for continuous learning as the models are constantly updated and improved using updated data sets from the clients. And this will help to achieve a higher rate of accuracy in the global model. Next, we'll be talking about our data set. So the data set that was used for our system was actually from Kaggle, comprising of a total of 11,801 images of radiography scans, in which 3,616 of them are for COVID positive X-ray scans, and 5,000 of them are for healthy X-ray scans, and 185 of them is for pneumonia. And this data set is actually acquired by a team of researchers from Doha, Qatar, and Dhaka, Bangladesh, Pakistan, and Malaysia. So for our system, we actually have 3 different clients. First is the client 1, which is actually we are training all the COVID models on this particular client. Client 2 is where we train all the healthy models, and client 3 is where we'll be training all the pneumonia models, and all these models will actually be sent to the server itself.
So to continue, this is our system architecture. We'll have 3 clients to simulate 3 different hospitals. These 3 clients will train the global model on their own dataset. So client 1 will train on COVID lungs images, client 2 train on healthy lungs images, and client 3 train on pneumonia lungs images. So once the clients have finished, the local model weights will be sent over to the server. At the server, it will perform federated averaging, combining all 3 models, and save it as a global model, and send it back to the 3 clients. So once the clients have received the global model, the clients will update the local model. This process will be iterated for a total of 3 times. So next, I'll now focus on the system flow of our federated learning. So, starting from the client, once the users start up the 3 clients, they will go into the user interface. There will be 3 buttons for the users, which are the train model, predict, and send model. So when user clicks on the train model button, it will firstly get the data set, then it will check how many iterations are there. If it's less than 3, it will proceed to check whether global model exists. If no, then it will start training the model. If yes, it will update with the global model. Once done, the system will save the model weights. So next, when user click on send model, the client system will start encrypting the model weights first, then send it over to the server. So once it reaches the server will decrypt the model, and the server will also check whether all 3 models have arrived. If not all arrive, the server will wait. So once all the models have arrived, server will perform federated averaging and save the global model and send it over to all 3 clients. So lastly is the predict button. So when user click on the predict button, the user interface will prompt user to input a lung X-ray image, and then after inputting, the system will predict the image using the global model, then output the predicted outcome. So this whole federated learning system, we have used TensorFlow VGG16 pre-trained model, Flask for the UI and the communication, and then cryptography FreeNet for the encryption and decryption. And so now I'll show the federated learning demo.
Thank you, Michelle, for the demonstration. Now, with a better understanding of our federated learning, let's take a look at our performance evaluation. The accuracy of our model is represented by the blue line. The accuracy of iteration 1 to iteration 2 is roughly the same, but a slight reduction from iteration 2 to iteration 3. This is because of the limited dataset that we have, and after aggregation, the accuracy seems to drop a little. The orange line represents the loss. There's a huge drop in iteration 1 to iteration 2, which is a good thing as this shows that the prediction is closer towards the class label. And from iteration 2 to iteration 3, there's not much difference. This shows that our model is stable. We also did a performance evaluation to compare centralized learning to our federated learning. For this, we used the MNIST dataset, which has 60,000 training dataset and 10,000 test set. We expected the centralized learning to perform better than federated learning, with the test accuracy higher by roughly 20% and test loss higher by roughly 33%. But with more iterations, we believe that the federated learning is expected to outperform that of the centralized learning. For future enhancement, we propose to add a couple more servers with load balancing capabilities to improve reliability and availability to our system, as currently we are only using one server. Finally, we also realized that our features of our dataset is not very distinguishable. We can improve it by adding more weights to specific pixels to these scans to distinguish the differences better. We can also change from VGG16 to convolutionary neural network to yield better accuracy, as the algorithm has the ability to learn relationship in the images based on the characteristics. That's all for our presentation. Thank you for your time.